History Feathers.
Hello and welcome to the special festive holiday fez version of a tutorial I'm going to do on uniform circular motion. This is actually a prop from the Buddy Faro TV show. Arena.
I think you're slime, Clancy, and you belong under a rock. And one of these days you're going to find yourself alone with me in an alley. No cameras, no policemen, no reporters. And then Buddy Faro's going to take you to school, teach you a few tricks. You jiggy with it?
He died this year, I think. I'm not sure. Not too long ago. Anyway. All right, let's take a look at uniform circular motion. When something is going in a circle, in uniform circular motion, uniform means that it's a uniform speed. Here's an object, let's say it's going around in a circle like that, and it's going to have a uniform speed. It's going to have a tangential velocity. Okay, tangential means, of course, it only touches one spot along the circle. It will always have a net force towards the center. If it's going in uniform circular motion, it's always going to have a net force towards the center. This is sometimes called the centripetal force, although I hate that term, F sub C, centripetal force. And it will also always be some other force. Now, it'll be a tension force or something like that. Now, since there's a net force towards the center, of course, the object is also accelerating towards the center. And sometimes we call that centripetal acceleration. That just means it's accelerating towards the center. And if it's in uniform circular motion, we know what the acceleration is what it is relative to the speed and the radius. The acceleration is v squared over r if it's in uniform circular motion. Okay, let me write that up there. So it's going around a circle. Now, what's causing this net force? It depends. It depends on what's going on. For instance, if in the middle we had the Earth, and that was a satellite going around the Earth, perhaps the moon or an artificial satellite, then bam! The net force would be the force of gravity, because that would be the only force on it, because if we circle it, we would see there's nothing in contact with the moon. It's out in space, and space is just filled with space. That's why it's called space. It's nothing but space. All right. Now, it wouldn't necessarily have to be. We have other problems with the uniform circular motion, not just planetary things or moonitary things. Sometimes we have cars going around in a circle. That's a car going around in a circle. It's going around in a circle. What is the centripetal force in this case? Bam! The centripetal force, of course, is friction. Friction is causing this thing to go around in a circle. That is the unbalanced force that is causing this to go in a circular motion. Or, of course, we could always have a situation where someone is spinning something on a rope or something like that, or like in our lab when we were spinning a stopper like that. There's our stopper. And in this case, with our stopper, the centripetal force, of course, is BAM! The force of tension on the stopper. Okay, so let's take a look. So centripetal force is just the net force on something in uniform circular motion. It could be multiple forces. In this course, we're not going to do multiple forces due to time constraints. Let's take a look at a gravitational problem. Let's say we have a planet. It doesn't matter what it is, a planet, and some satellite going around the planet in uniform circular motion. Let's find the relationship between the period of rotation and the radius, okay, of rotation. Radius, okay, and in all our distances in gravity will always be measured from center of mass to center of mass, and certainly radius will be measured in those terms. So we have something going around a planet, and we want to analyze it. Of course, we want to know something about motion and we know something about forces, so we're going to apply Newton's second law. I'm going to circle the object of interest. I see that there's nothing in contact with it. There are no contact forces. Of course, there is the force of gravity. Let's draw a free body diagram, and there's a force of gravity this way, and that is the only force on the object, so therefore it must be the net force. So Newton's law says the sum of the forces, the vector sum of the forces, equals mass times acceleration. All right, so that's the mass of S. And using the universal gravitation equation, the sum of the forces is just going to be the force of gravity, which will be G, mass of P, mass of S, divided by R squared, and that will equal mass of S times the acceleration. But in uniform circular motion, the acceleration of an object is V squared over R. All right, let's cross those out. Okay, we can cancel those puppies out. They're all canceled. Now, right now we have, and we can get rid of one of our radii here. Now we have radius in terms of velocity. So let's get this in terms of the period. Kind of running out of room. Let me take this here, erase that, and let's remind ourselves when we have a velocity, that of course is defined as distance divided by time, at least average velocity. And since it's constant velocity, then that's just the velocity. Actually, it's not the velocity, it's the speed. I'm sorry. I shouldn't have said velocity, I should have said speed. The speed is distance over time. So anyways, the distance, when circular motion, the distance around a circle is 2 pi r, and the time to go around once is defined as the period. So the speed equals 2 pi r over capital T. All right, well, let's substitute that in here, and we'll get this relationship. Universal gravitation constant times the mass of the center object, in this case a planet, or it could be a star or something like that. The distance between them, and V squared, which is going to be 4 pi squared R squared divided by T squared. All right. So let's, all right, so why don't we put it, we can put it in many terms. Let's get T squared by itself. We could say T squared equals 4 pi squared over G MP R squared. All right. Now we notice this right here is a constant. 4 times pi squared times the universal gravitation constant times the mass of the planet, which we assume stays constant. Oh, we forgot to bring the r over. That's r cubed. That's not r squared, that's r cubed. We forgot that one over there. So we see that the period squared is proportional to r cubed. This is Kepler's third law of motion. Okay, not so important to know that, but that's just a nice thing to know. It's just bring it up at parties, especially festive holiday parties. You'll be the belle of the ball, so to speak. All right, so there we've applied Newton's second law to a uniform circular motion problem, and we got this nice relationship. We could have done something similar with a car going around in a circle, in which case, instead of this being the force of gravity, this would be friction, and we have relationships with friction and stuff like that. Well, anyways, that's a quick little lesson on uniform circular motion. Hopefully that cleared some things up, or not. If not, at least you got to enjoy the Fez. Happy holidays!
Extreme Fez.